ME204, Relative Motion Analysis of Rigid Bodies. We've already talked about the fact that general plane motion involves both translation and rotation, and we've talked about absolute motion analysis as a method to solve these types of problems. Today we want to talk about relative motion analysis as a method for solving general plane motion problems. In order to solve relative motion analysis problems, we need to understand vector cross products. What is a vector cross product? Well, it's a method of multiplying two vectors together, resulting in a third vector that is perpendicular to the plane formed by the first two vectors. For example, if I have two vectors, vector A and vector B, represented by vector A being 3i plus 5j minus 6k, and vector B being equal to minus 2i plus 4j plus 1k, and I want to determine the cross product of those two vectors, I want to find A cross B. We say this as A cross B, not A times B, but A cross B. In order to find the cross product of A cross B, I just set up a matrix and find the determinant of that matrix. Here's what my matrix will look like. The first row will be I, j, k. The second row will be the components of vector A, 3, 5, and minus 6. And the third row will be the components of vector B, minus 2, 4, and 1. Don't forget to put the alternating signs on the top row. It's positive for I, negative for j, and positive for k. To solve this, we first need to look at the I component. For the I component, we're going to cross out the row and the column that are in line with I. Then, in this case, we'll multiply the 5 times the 1 and subtract from it the negative 6 times the 4. That will give us the I component for the cross product, which in this case is 29i. For the j component, first we have to remember that the j is negative, so we'll put a negative j in there, and we'll cross out the row and the column in line with the j. Then we repeat the process that we had with the I component. We'll multiply the 3 times the 1 and subtract from that a minus 6 times a minus 2. That will give us the j component, which in this case is 9j. For the k component, we cross out the row and the column in line with the k. Then we multiply the 3 times the 4 and subtract from that the 5 times the minus 2. That gives us the k component, which in this case is 22k. So the cross product of A cross B will give us a vector that's equal to 29i plus 9j plus 22k. Let's review rotation about a fixed axis. This is something that we'll also use when we look at relative motion analysis. If I've got a rod here that's 3 meters long and rotating at 5 radians per second, what is the velocity of point B? And let's write that as a vector. Well, we know that the velocity is equal to the angular velocity times the radius, which in this case is 5 radians per second times 3 meters, which would give me 15 meters per second, and we know that it's all going to be in the j direction. What if we're at an angle? Let's determine the velocity of point B and write it as a vector using the scalar method, or the same method we did in the previous example. In this case, our velocity again is equal to our angular velocity times the radius, which is 5 times 3, which equals 15. We need to break it into components to write this as a vector. Our velocity in the x direction will be equal to 15 times the sine of 30, which is 7.5. And our velocity in the y direction is 15 times the cosine of 30, which is equal to 13. So my velocity vector becomes 7.5 meters per second in the I direction plus 13 meters per second in the j direction. Well, is there another way that we can do this? Let's determine the velocity vector of point B using a vector cross product. In this case, our angular velocity, omega, is coming straight out of the page. It rotates about the z-axis. If the x and y-axis form the plane that we're looking at, then the z-axis comes out of the page towards us or into the page away from us if it's negative. In this case, if we use the right-hand rule And notice that our 5 radians per second is rotating clockwise, then our angular velocity is a negative value. So our angular velocity vector becomes 0 in the I direction, plus 0 in the j direction, minus 5 in the k direction. Our radius vector is the radius of our rod from A to B broken into components. We have an x component and a y component. If the origin is at A, then the x component is negative and the y component is positive. In this case, 3 times the cosine of 30 gives us a negative 2.6 in the I direction, and 3 times the sine of 30 gives us 1.5 in the j direction. And it's all in the xy plane, so there's nothing happening in the k direction. So my radius vector becomes minus 2.6i plus 1.5j plus 0k. If we take the cross product of these two vectors, we can determine the velocity vector. So the velocity vector is equal to the angular velocity vector crossed with the radius vector. Let's set up our matrix and run this cross product. In the I direction, we would get 0 times 0, which is 0, minus a 1.5 times a minus 5 in the I direction, plus a negative for our j direction, as we can see here, a negative 0 times 0, which is 0, minus a minus 2.6 times a minus 5 in the j direction. And in the k direction, we have 0 times a 1.5, which is 0, minus a 0 times a negative 2.6, which is also 0. So my velocity vector becomes 7.5 in the I direction, plus 13 in the j direction, plus 0 in the k direction. Notice that this is the same velocity vector that we obtained by just using v equals omega times r and breaking that into components. Now let's talk about relative motion. We've discussed relative motion before, and we looked at a school bus as an example. If we're riding on a school bus and someone runs down the middle of the aisle at 5 miles an hour, how fast is that person actually traveling? Well, from someone standing on the side of the road watching the bus move by at 55 miles an hour and the boy running at 5 miles an hour down the middle of the aisle, we can figure out that the boy is going at 60 miles per hour. How do we determine that? Well, if we call the bus A and the boy B, we use our relative motion equation. The velocity of B is equal to the velocity of A plus the velocity of B relative to A, or velocity of B from the perspective of A. The same is true for relative motion. Let's look at this ball. This ball is translating and rotating at the same time. So how fast is the top of the ball moving as it goes across the page? We can look at translation and rotation separately and then add that motion together to get the complete motion. So if we look at just the translation and then add to that the rotation, we can get a characterization of the motion. We do this using superposition and our relative motion equation. First of all, let's look at the velocity due to the translation only. The center of the ball, velocity c, is 5 meters per second. That means that as the ball is translating, any point on that ball travels at the same speed. But for this case, we're going to look at just the velocity of the center as being 5 meters per second. We're going to add to that the velocity due to the rotation of the ball only. This is the velocity of the top of the ball from the perspective of the center of the ball, or relative to the center. We can determine that by fixing the center of the ball and spinning the ball about that point. We can find the velocity of the top from the perspective of the center by using our velocity is equal to the angular velocity times the radius, in this case 50 times 0.1, which would give us 5 meters per second. Finally, we add the translation and the rotation together to get the velocity, the actual velocity of the top of the ball. In this case, the velocity of the top is equal to the velocity of the center plus the velocity of the top from the perspective of the center. Notice that the velocity of the center is our translation, and the velocity of the top from the perspective of the center is the rotation. Our velocity at the top of the ball is equal to 5 plus 5, which gives us a velocity of 10 meters per second. Let's assume that this rod is spinning and moving through the air at the same time. It's translating and rotating, something like this. How do we characterize that motion? Again, we can look at the translation and rotation separately and then add them together to get the complete motion. So we could look at the rotation and then the translation, and we end up at the same position. And so we can characterize those motions separately to get the same result. Again, we'll use the method of superposition. Let's look at the velocity due to the translation only. Well, we know that the velocity at A is 4 meters per second. That also means that at any point on that body it's translating at the same rate. So at B, the velocity is equal to 4 meters per second, which is the same as the velocity at A. This represents the translation only. We can then break that into components, with the x component being 3.5 meters per second and the y component being -2 meters per second. Let's write that as a vector. The velocity of A is equal to 3.5i plus a -2j plus a 0k. The velocity due to rotation only is represented by fixing our rod at point A and characterizing the rotation about that point. So at point B, the velocity at B from the perspective of A is equal to r omega, 5 radians per second, times our radius, which is 3 meters, to give us 15 meters per second. We can then break that into components with 7.5 in the x direction and 13 in the y direction. We could also use the cross product to solve this. The velocity of B from the perspective of A is equal to the angular velocity of AB crossed with the radius to B from A, or the radius of B from the perspective of A, or the radius of B relative to A. Notice that the position of the radius vector is the location of B from A, and is written the same way as we would write our velocity in our relative motion equation, the velocity of B from the perspective of A. This direction is important in making sure that our signs come out correctly. Negative in the x direction, positive in the y direction. Our angular velocity is 0 in the I direction, 0 in the j direction, and -5 in the k direction. And our radius, 2b from A, is -2.6 in the I direction, plus 1.5 in the j direction, plus 0 in the k direction. We already took this cross product previously when we looked at this rod as a fixed rotation about A, and found that the velocity of B from the perspective of A is equal to 7.5 in the I direction, plus 13 in the j direction, plus 0 in the k direction. To get the velocity due to both the translation and rotation at B, we look at the translation and add that to the rotation to get both. We can use vector addition to accomplish this. So the velocity at B is equal to the velocity at A plus the velocity at B from the perspective of A, with the velocity of A being our translation and the velocity of B from the perspective of A being the rotation. Our velocity at B gives us both the translation and rotation added together. So we simply do vector addition to obtain our total velocity vector. So the velocity at B becomes 11 in the I direction, plus 11 in the j direction, plus 0 in the k direction. The magnitude of this velocity is the square root of the sum of the squares for this vector, which is equal to 15.6 meters per second. Now let's look at our example problem again with our hospital bed that's being raised by the moving roller at A. We already looked at this using absolute motion analysis, but let's see if we can solve this same problem using relative motion analysis. We know that at point A we're moving at 0.5 feet per second to the right, and we want to know how fast the bed at B is rising. Our links are 4 feet long, and we're going to develop this as a function of theta. The velocity at B is equal to the velocity at A plus the velocity of b from the perspective of a. First of all, our velocity of a in vector notation is 0.5 feet per second in the I direction, and it's positive because it's moving to the right. The velocity of b from the perspective of a, or the rotation of that member, is equal to the angular velocity of BA crossed with the radius vector 2b from the perspective of A, which will give us a radius vector that is positive in both directions. In the x direction, it will be 4 times the cosine of theta, and in the y direction, 4 times the sine of theta. So we get a radius vector of b from the perspective of A equal to 4 cosine of theta I plus 4 sine of theta j. We don't know what our angular velocity is, so we're just going to go ahead and put that in symbolically as omega BA. If we write our cross product vector to determine the velocity of b from the perspective of A and calculate the determinant, then we find that the velocity of b from the perspective of A is equal to, in the I direction, 0 times 0, which is 0, minus omega BA times 4 sine of theta in the I direction. We place a negative sign for our j direction and get 0 times 0 minus omega BA times 4 cosine of theta in the j direction. In the k direction, we simply have a 0 times 4 sine of theta, which is 0, minus 0 times 4 cosine of theta, which is also 0, so we don't need that k component. The velocity at b, then, is simply determined by placing our velocity of a vector into our relative motion equation and our velocity of b from the perspective of a vector into our relative motion equation and adding those vectors together. The I components then become 0.5 feet per second minus omega BA times 4 sine theta in the I direction plus omega BA times 4 cosine of theta in the j direction. We know that the velocity of b in the x direction is 0 because it's traveling straight upward. So we can take the I component of our velocity in the b direction vector and set that equal to 0. So 0.5 minus the angular velocity BA times 4 sine of theta is equal to 0. Solving this equation for the angular velocity BA, we obtain that the angular velocity BA is equal to 0.5 feet per second divided by 4 times the sine of theta. We can then look at the y component of the velocity of b. So the velocity b in the y direction is equal to our angular velocity BA times 4 cosine of theta. That's simply the j component of our velocity vector. And knowing the angular velocity for BA, we can substitute that into our equation to get that the velocity of b in the y direction is 0.5 feet per second times 4 cosine of theta divided by 4 sine of theta. The 4's cancel, and the cosine of theta over the sine of theta becomes the cotangent of theta, which gives us a velocity of b in the y direction equal to 0.5 times the cotangent of theta, which is the same result that we obtained in the absolute motion analysis method. Let's review the steps for relative motion analysis. Our first step is for a single rigid body. Now sometimes we'll have multiple rigid bodies, and for each body we need to move through this process. So we choose a single rigid body and choose a point on that body where there's some known information, typically a velocity. In this case, let's say the velocity at A. Second, we relate the known point, the velocity at A, to another point on the rigid body, for example, the velocity at B, using the relative motion equation to include both the translation and rotation, and we'll use vector notation to do this. So the velocity vector at A is equal to the velocity at B plus the velocity of A from the perspective of B. Note that the velocity of A from the perspective of B is the rotation, and the velocity of B is the translation. Next, we determine the distance between the known and unknown points in vector notation, the radius of A to B. Be sure to use the correct signs to represent the direction. In this case, the distance from B to A, or A from the perspective of B. So the radius of A from the perspective of B is the radius of A from perspective of B in the I direction, plus the radius of A from the perspective of B in the j direction. Fourth, we calculate the velocity due to pure rotation using the cross product of the angular velocity and the direction vector. So the velocity of A from the perspective of B is equal to the angular velocity of AB cross the direction vector of A from the perspective of B. In this case, we'll have a matrix of ijk, 0, 0, omega, and the radius of A from the perspective of B in the I direction, radius of A from the perspective of B in the j direction, and 0. And then we would solve that cross product. Once we have our cross product, we add the velocity due to pure rotation to the relative motion equation and solve for the unknowns. And we would separate that into components to solve this problem if necessary. Once we have all of our unknowns determined, we can use the calculated information to move to the next connected member and repeat the process until we move through all the parts of the simple machine. Our next topic is instant center analysis of rigid bodies.